TUBS-IRMB. Digital India. Educated India.
Yeah, welcome to lecture number 7 of this GIAN course of high fidelity lattice Boltzmann methods. So this is now a little bit in exchange to the actual planned hands-on session, which we'll do instead tomorrow all together. So we replanned this, and this is a good thing actually, because today we'll talk about the initial and boundary conditions, which of course are required in order to do actual simulations. So before we can talk about how to set initial and boundary conditions, we of course have to deal with the question how we actually set these values, because we had this discussion that in the lattice Boltzmann world we always have to use this lattice unit. So we assume that delta x, that velocities is given in delta x by delta t, and pressures are given by delta x square by delta t square divided by a standard density. So this means we have to discuss how these things translate to the real world. So scaling of units. And here's given, so assuming we know what delta x is, so delta x is coming in meters, and we have a given delta t, which has the unit seconds. And we'll always use the variables without star as the dimensionless, so the dimensionless version, so the ones that we are using in our code. So this would be the dimensionless velocity. And we would use u star as the dimensional velocity. So dimensionless, we also call this lattice units. So then u is basically the physical velocity now that we have to translate into the lattice velocity, which we do by introducing delta t, divided by delta x. So these, of course, come in their physical units, and then we get to the velocity that we have. So, for example, say that delta x would be 1 millimeter and delta t would be 1 microsecond. And our velocity that we have to deal with in the real world is 0.1 meters per second. Then the velocity that we had to set in the lattice Boltzmann world would be 0.1 meters per second times 10 minus, 10 minus by the power of minus 6 seconds divided by millimeter is 10 by the power of minus 3 meters, and this should then translate to 10 by the power of minus 4, and this will then have no further units. Okay, velocity is pretty simple. A little bit more complicated is potentially pressure. So lattice pressure. So since we simplified our Boltzmann equation that much, we have to accept that we are now in a pseudo-incompressible version, so that we can only work with very small variations of pressure. Small pressure differences. And this is actually also true for the Navier-Stokes equation, yeah? So in the Navier-Stokes equation, pressure is a potential. When potential can go, actually pressure is not really a potential, but in the Navier-Stokes equation, it kind of is. You see, in the Navier-Stokes equation, pressure can go, because it's a potential, you can have an arbitrary level, so it can go arbitrary to a negative infinity, yeah? But at the moment where there is no more material, then there should be no more pressure. Yeah, so somehow this nonlinearity escapes from the so got lost, yeah, in the truncation of the Boltzmann equation. So what is actually pressure? There is a bit is a kind of a little bit illogical, and there's also still discussion going on, because the pressure, or let's face it this way, what moment is a pressure? Can you give me a guess? So the first moment is the velocity. Which moment is pressure? What is pressure related to? Energy, internal energy, right? So then what moment would it be? So it would be a second moment. Yeah, it is also correct. It is a second moment. But this is not the way it is treated in Lattice-Boltzmann. So in Lattice-Boltzmann, there is a simple equation of state, yeah, saying that volume is so the temperature is constant, yeah. So PV is pressure times volume is constant, and then you have a particle density, and this particle density therefore is proportional to the pressure. Yeah. So later, when we do the asymptotic analysis again, we'll see that actually the pressure in the Navier-Stokes equation arises from the second order moment, but it arises from the equilibrium of the second order moment, and the equilibrium of the second order moment depends on the zero moment, yeah, through this equation of state, such that we assume, not completely correctly, that the zero order moment is equal to the pressure. Actually, not equal to the pressure, but equal to 3 times the pressure due to the speed of sound. So the assumption here is that M00, yeah, this is what we call rho, and this can be related to the pressure, or a small difference in pressure, which I call here delta P. So this is the small variation in pressure. This has to be rescaled with, I just found that I had forgotten this. So with the speed of sound times the physical density so a physical standard density. So the density of the fluid, which we assume does not vary very strongly. And this has to be scaled by dt squared delta t squared delta x squared, because pressure is, as you said, proportional to energy and therefore to velocity squared. Yeah, and this also means that we have to that it scales like it basically scales like the velocity squared when we translate it to physical units. And this, of course, if you see there's a small variation of this, this would mean that rho would be something around 0, which it is, of course, not. So we have to add a 1 here. So that's, you know, okay. So originally, I don't know whether I said this. So a 0-order moment for probability density function should actually be always be 1. Yeah, because the distribution is normalized such that when you integrate over the entire universe, or say, you know, you're looking for a particle and you say, is it in the universe? Then the likelihood should be 1. Yeah, otherwise it would not exist. Therefore, the entire mathematics that is behind this probability computation is always based on the assumption that the integral over the entire distribution function, which is the 0-order moment, is 1. This is, in Lattice Boltzmann, now not directly the case, because we also assume that particles could be in another place on the lattice, yeah, so that there could be fewer particles, or the probability of a particles being there could be smaller. Therefore, this is a non-normalized distribution function, and this is, for example, also the reason why when we factorize the equilibrium function as we did yesterday, we always have to divide by rho, yeah, because usually this factorization of the moments would hold without this additional normalization, because the distribution function usually would already be normalized. Okay, so yes, so this rho star here would be the mass of a particle divided by the volume that is occupied by a particle, right? So this is the standard density. So let's now use these things to, okay, so this is the recomputation, the scaling of the variables, and now we want to set, for example, initial conditions. Okay, we call the initial conditions IC. So there is a difference from these initial conditions and the initial conditions that we use in the Navier-Stokes equation. Here we require initial conditions for all moments, or you could equally say for all populations, the entire distribution functions. Whereas in the Navier-Stokes equations, we only need them for U star, and so in the Navier-Stokes equation we only have to initialize U, velocity, and pressure. That's all. However, here in the Lattice Boltzmann world, we have to have more moments. So where do we get all these moments? The easiest and I guess still most common way of doing this is the so-called equilibrium method, which is pretty simple. So suppose we have the initial conditions that we would use in the Navier-Stokes equation, say a velocity at time 0 and distributed over space, and rho at distributed over space and at time 0, then what we can do is we can compute the local equilibrium Fij equilibrium for this given velocity and the given density or mass, and we can do this from the Maxwell moments, or actually from any of the ways to compute the equilibrium function that we have seen this morning. You should usually use the one that you use in your code. Yeah, that's a little bit more consistent. So, is this a good thing? Nabla smiles. This works. This is simple. This is, can we give a thumbs down? This is inconsistent. Inconsistent, in particular for second moments. You know, it's funny that I say it works and then I say it is inconsistent. Now, when things, you know, it always depends on what is your intention, what do you want? And very, very often, you're looking for a final outcome that has nothing anymore to do with your initial conditions. So whenever, so I mean, you anyway have to set some initial conditions. Say you want to measure the drag on a car. Then you set any initial conditions. Then you let the thing run and wait until you have enough statistical data. So after the flow is developed, and then you collect statistical data, and then you measure the drag and lift coefficients, and then you report this to your master engineer, right? So in this case, you don't care a lot about the consistency of your initial conditions. They may be inconsistent anyway because you start from velocity 0 or something, yeah? So when would the initial conditions, the consistency of initial conditions really matter? If you have a time-dependent solution, correct, yeah? If you have a time-dependent solution and you really want to know what happens in the first few moments of your simulation, then you need to have a consistent initial condition. So, right, because what we observe here is that we have wrong dissipation in the start of the simulation. So, therefore, you would like to use second moment non-equilibrium I need to protect this. Second moment non-equilibrium initialization. Okay, let's remind us. So the Navier-Stokes limit, in which we want to solve our approximation of the Boltzmann equation, requires second order moments to be second order accurate. Second order accurate in a smallness parameter that we identify with delta x. And third order moments to be first order accurate. I'm wondering whether accurate is potentially okay. If you don't mind, we rather write consistent. If I can write consistent, and first order, the other one first order consistent. So I'm taking a little bit from picking from something that I've not yet explained in that detail. We decided that we first talk about boundary conditions and initial conditions before we make the last step in the analysis, which is the asymptotic analysis, which we'll talk about on Monday. Yeah, so then it will be coming absolutely clear why the second moment needs to be in second order and the third moment needs to be in first order. You could also see this roughly in the analysis that we had so far, but they have not been so detailed so far. So again, so I'm taking this a little bit. So we'll discuss this a little bit in more detail on Monday. But the non-equilibrium part of this second order moments would include, so of course the moment itself would include the equilibrium, but it would also include viscosity, with the viscous part, which is this here, including this part here and the derivative in x, this times rho. So we have seen this already in deriving the one-dimensional form of the Navier-Stokes equation from our model. Yeah, the only thing that I think we have not yet detailed on. So this is, we have also seen that the viscosity get transformed into this. Yeah, but on Monday we will repeat this with a more precise method again, where if you now don't remember this will come up again. Yeah, but in order for having it for the coding tomorrow, we decided to present this before. So the same thing goes like this. So the other second moment has its equilibrium part minus 1 over omega minus 1/2. This is the Eon correction into 2/3 dy/v, and this also multiplied with rho. And then there is the third one, this m11 is equal to m11 equilibrium minus 1 over omega minus 1/2. And this goes into, I think I write the 1/3 here in front, dx v plus dy u times rho. So somebody asked me whether you can determine the derivatives from the moments. Yeah, so this is the derivatives from the moments, and you also, if you want to set them, you also have to set in the beginning the particular gradients here. So third order is then simple because third order only requires equilibrium, because they only need to be first order accurate. So it's sufficient to say that M12 is equal to M12 equilibrium, M21 is equal to M21 equilibrium. So this is sufficient for the initialization to be consistent. So of course, we cannot set the M over bar because we don't have them in our code. What we have is the pre-collision state, and the pre-collision state, now it depends on, so IC for pre-collision state. So yesterday somebody asked me, is it important to start with a collision or is it important to start with a streaming? So if you start with a collision, then you have to set your initial condition for the pre-collision state. If you start with a streaming, you have to set your initial condition for the post-collision state. Yeah, that's, I guess this makes sense. So now I'm assuming that we start with a pre-collision state, and when we start with a pre-collision state, then this M20 becomes M20 equilibrium minus 1 over omega rho, 2/3 dxu M02 equals to M02 equilibrium minus 1 over omega rho 2/3 dyv. Did I make it? Yes. And the last one, M11, is M11 equilibrium minus 1/3 omega rho dx v plus dy u. Actually, can you give me, from this information is actually enough to determine what the equilibrium of the post-collision state would look like. Can anybody guess this? You may use the microphone.
Can we set left hand to equal to 0, left hand side?
The left hand equal to 0. What's left hand? So I mean, how you want to set the left hand of what to 0?
I mean, M20 or M11.
M20
We need post collision, right?
in the post collision.
No.
You mean the post collision is equal to 0?
No. What I mean is post collision M20 should be equal to M20 equilibrium, right?
So, okay, I mean, M20 post collision is equal to
M20 itself.
M20. Why?
Because the collision operator has to be 0, right? After collision.
The collision operator has to be 0. Well, why would the collision operator be 0? Okay, I give you a hint. M over bar is the average between M before collision and M after collision, right? So there needs to be something that I add to this and divide by 2 in order to end up here. What would that be? Okay, I guess there would still be equilibrium because this is here and here, right? So there's still this part here because we have this 2/3 dx u times rho. This we also have there and there, but we have it with a different prefactor. So and there would be a minus still. So now it needs to be a different prefactor. What prefactor would that be? Minus half of what? M2. Okay, I don't hear. Maybe.
Minus half of that 2/3.
Minus half of the 2/3. Okay, minus half. No, minus half. So should I write minus half?
No, it's okay.
Okay, let's go on. We have 1 over omega here, and we have 1 over omega there. Yeah. If we add them together and divide by 2, we end up with 1 over omega. So then we have minus 1/2 here. That would be minus 1, right? So that if we add this to this and divide by 2, yeah, then we would have this. So this is if you want to do it for post-collision, if you want to initialize for post-collision, you would need to use this version. Yeah? Other color. Okay, so this is the initial condition. Relatively straightforward. Then comes the boundary condition. So boundary condition actually can mean everything and nothing. Boundary conditions. So we call them BC, boundary conditions. And here the important thing is that the boundary conditions that we have for the Navier-Stokes equation, they are not consistent or not compatible with the LBM, because LBM requires more information. We cannot set the boundary condition on U and P, because U and P are emerging quantities of the distributions. We have to set the distribution in order that we get what we want. Yeah. So we have to set BCs for populations, or sometimes we can also set them for the entire distribution. So now, you know, if you have nothing better to do in your life and you want to become a scientist and want to write papers on Lattice Boltzmann, and you have to write papers for Lattice Boltzmann to proceed as an academic, then you invent a new boundary condition and you write a paper on this. So there are two such things. Either you invent a forcing scheme or you invent a boundary condition. And then you write your thesis, and then we're stacking up boundary conditions and forcing scheme and forcing schemes. And in a sense, this annoys old people like me, because it all implies that that all of this would be so terribly difficult, that we need more and more boundary conditions, and more forcing schemes, which is mostly not true. So I can now spend the rest of the entire next week just on boundary conditions. So I'll leave out a lot here, what we could actually talk about, and also many things that you will find in the book, and that I find strangely popular with students, even though they often end up using strange boundary conditions that are much older than the students themselves and don't work very well. But I will just give you a few, and I will start with some basic distinction here. namely the distinction between node-based and link-based boundary conditions, and they may also be called wet and dry for whatever reason. And the distinction here is the following. We are using our characteristic diagram. This is very useful today, where we have here x and here t, and say we have these nodes. So, and now we assume on this so-called wet boundary conditions, let's have them in blue. On the wet boundary conditions, that the boundary is actually on the node. So here we have a boundary. So this kind of thing you'll often see in particular textbooks. This potentially also means that it is what ChatGPT knows the best of. So they have been very popular, in particular in the beginning of the Lattice Boltzmann world, so actually in the last century, kind of. It has been relatively soon observed that that most of these boundary conditions are not very stable. They are orientation dependent. Because you see it depends which direction is incoming and which direction is non-incoming, and also if you are on an edge or in a corner, they will behave differently because you have more or less. So you can have a convex corner, you can have a concave corner, then you have more incoming populations or fewer incoming populations that you can treat to solve your problem. So I think initially, yes, and I said they are difficult. I should also say they are difficult to generalize. So, and they origin actually a little bit from the idea that everything goes on the nodes, on the nodes. So you would like to set your boundary conditions directly on the nodes, and you would want to set directly your whatever velocity or pressure, in particular on that node. So I decided not to show now any of these examples. You will find them in the books if you like them. There's boundary conditions Souhet. There's by Souhet there is boundary conditions by Bennett and Rees that use this wet configuration. With these boundaries conditions, you of course always set the boundary condition on the node, yeah. And this is a little bit against the thinking that we have developed, that we store actually our populations all the time somewhere in between, yeah, in between the time step and in between the grid nodes. So, and this is the alternative to this boundary conditions, and somehow because this better fits in the Lattice Boltzmann world, this is also something that is found to be working much better, usually is easier to implement, and usually is much more stable. So what do I mean? Now let me draw here a cross and say we are now not assuming to put the boundary on the node, but we put the boundary in between the nodes. Meaning we have here, for example, let me take another color. Yeah, something going in here and something going out here. So we would have the boundary condition, yeah, not on the node, but on this link, so on this one population at this intermediate time and in this intermediate space. So we'll assume that the one that is going out is called Fi and the one that is coming in is F minus I. And here we put the boundary on the link. And this would usually imply that it is halfway in between. Halfway between two nodes. So the very simplest boundary condition that you can imagine is if you just return in the population that went out, if you just return this leads to the simple boundary condition that we call the halfway bounce back. Boundary condition. This is when Fi at the position, so in the last position. So say this here is, what did I call this? So this is xn. So fxn at the next time step, t plus delta t, is equal to, so this is the incoming, the pre-collision state, is equal to the post-collision state before at the same position. Yeah, we simply return this here. So what boundary condition does this imply? This implies a boundary condition of zero slip, so bounce back is a no slip boundary condition, so it's a velocity zero boundary condition, and it is a boundary condition that conserves mass, right? Because whatever goes out goes straight in again. Yeah, so you're not losing any mass. So this is, for example, so you get, if you use just this sort of boundary conditions, you get along in the lattice Boltzmann methods without a Dirichlet boundary condition for the pressure. So this is, by the way, the reason why, one of the reasons probably, why this lid-driven cavity example is so popular in lattice Boltzmann, because it's actually a strange thing, because it's a closed box and you can simulate this entirely with a bounce back boundary conditions, which is conservative boundary conditions. You do not need to specify a Dirichlet boundary condition on the pressure, yeah, because the mass in the domain is conserved. In almost all other cases, you will have to specify a Dirichlet boundary condition for the pressure. Okay, so then many other boundary conditions arise from the bounce back boundary condition. One modification is the so-called delayed the delayed bounce back. So this is not much different. It's just the following. So we have here t. Again, we have here x. These are our nodes. And here's our wall. And let's go a little bit further. So in this bound, maybe I draw this here in a more in this way like this. Yeah, so this comes back at the same time step. So it just at the next time step is already coming back. Yeah. Whereas in the delayed bounce back, what happens here is that the population leaves the domain, goes to the outside node, and then comes back a time step later, which means fortunately I'm running out of digital ink. See, I need a dip for the ink. Which means we can write this fi now as x, so again this here is xn. xn t plus now 2 delta t is equal to fi asterisk xn and t. So why do we do this? It simply has been observed that adding this delay helps to eliminate grid scale oscillations. So we are very wary of instabilities in the lattice Boltzmann methods, yeah, because we want to simulate turbulent flow, yeah, meaning at very high Reynolds number, and there we can easily trigger oscillations. Using these boundary conditions together with a delay is actually able to suppress some oscillations and therefore make the simulation more stable. Yeah, so this is one of the dirty tricks that you will probably not read in the books because it's not. I always think this is not talked about a lot because it does not put lattice Boltzmann in the best lights. Yeah, so that I mean, it sounds like that this delay is a little bit, artificial, yeah, and you should avoid it. And the other version is physically more sound, but this works better. Okay, little trick. So now you could say we have seen only bounce back, and I just said this lid-driven. A lid-driven cavity. I don't know whether we talked about the lid-driven cavity. I don't think so. So lid-driven cavity gives you, this a cavity that is closed, and on the top you have a lid that is driving. Yeah. So now how can we put this just with bounce back? Yeah. Obviously, we have 3 non-moving walls, but we have a moving wall on top. Yeah, and if you think about this no-slip boundary condition, you see that this is a velocity boundary condition. It's just a velocity boundary condition fixed at velocity 0. And therefore, we can ask, when it works for velocity 0, can we make it work for another velocity 2? And yes, this is very, very easy. So we have velocity bounce back velocity bounce back. This is very simple, a bounce back boundary condition, xn t plus either delta t or 2 delta t, so you can decide what you like, delayed or non-delayed, yeah, is equal to fi star xn and t. So this is the bounce back, yeah? And now what we do on top of the bounce back is adding a shift in velocity. And the shift in velocity goes like this. It is 2 times minus 2 times theta wi ei. This is the direction of this link showing into the boundary times a scalar product, the velocity at the boundary that we want to specify. Yeah. So basically, this theta is 1/3. Yeah, this theta is 1/3. I was just thinking, is it okay? Now the stupid professor is just starting to think whether it is theta or 1/theta. I think this is the right way. Anyway, so there's a prefactor that we need, and what this basically does is adding or subtracting the velocity of the moving object twice. Yeah, I mean, you have heard that you have a momentum exchange with a wall. Yeah, you throw a wall against you throw a ball against the wall, and it's coming back. Then it means it has given twice the momentum of the ball to the wall, so that it can return with this particular velocity. And here we are turning things around, so we add twice the scaled velocity, yeah, scaled by some function in order to return this. So is this now to set the velocity there? So question: is this thing conservative? I mean, you think back what I told you just, that the lid-driven cavity is a conservative, uses only conservative boundary conditions, so this needs to be conservative. So why would this be conservative? Okay, that's this here that you add. So this alone, this would be conservative without the added velocity, right? Okay, what do I mean with conservative? Mass conserving, not momentum conserving. Yeah, I mean, this is an important thing, that how does the no-slip boundary condition conserve momentum? You know, a no-slip boundary condition is not supposed to conserve momentum. Yeah, so this is supposed to, boundary conditions in general are not supposed to be conservative. They communicate with the outside world. Yeah, but they can, for example, be conservative with respect to mass, because they only transfer momentum, but they should not transfer mass. So does this thing here transfer mass? So this here in front does not transfer mass to the outside world. This here, of course, transfers mass to the outside world. However, when you have a node here, so then it will have a link in this direction, and it will have a link in the opposite direction. Oh no, I forgot. Okay, so it will have a link in one direction, and it will have a link in the other direction. And when the velocity in both places is the same, right? So then we lose mass in one direction, and we are added the same mass in the other direction, because this here does not depend on anything that is going out. It's only depending on the velocity. So you need to have a consistent velocity field on your boundary, and then it is conservative for mass. If you have an inconsistent velocity field on your boundary, then it may not be conservative for mass. And this, okay, so this was assuming a velocity horizontal to the domain. When you have an inflow or an outflow, so velocity is going normal to the boundary, then of course you don't want to have mass conservation. I mean, when something is flowing in, then it's not supposed to be conserving mass, right? Okay, good. So this means we can do solid walls, we can do any velocity boundary condition. The only problem that we have is now we can place these boundary conditions only always halfway between grid nodes. So then one thing that is missing is the pressure boundary condition. Pressure boundary condition. There are different ways to impose these. We'll talk only about one, and this is the anti-bounce back. So we learned about bounce back, now we learn about anti-bounce back. Anti-bounce back, what is this? So we have F in the incoming direction at the position, say, at the first nodes at the entrance at a later time step. And here we have again the outgoing population, X and T. So this is bounce back. So how do we make anti-bounce back? We make anti-bounce back by saying we put a minus here. Yeah? So instead of taking this population in, is we eliminate this population, and then we have to add in its stead Fi eq u bc. So we need to know a velocity on the boundary. This is not necessarily easy to know. Then we have the density on the boundary. This is density. I said that density is related to the pressure. So this may be the pressure that you want to set on this particular boundary. So, and this together with the, so this is Fi. This is the direction that goes out of the domain. F minus I is the direction that goes into the domain. And we have set here the equilibrium of the one that is going into the domain. So this is a dot, and this here is an overbar, minus. And here we set the same boundary condition, the velocity, and rho bc. And this is the anti-bounce back. Okay, so I know it drops a little bit from the heaven, yeah, but the difference, what the thing does is this bounce back, the bounce back boundary condition, this, if you think about it, the bounce back boundary condition sets a first order moment, right? So if you rewrite this boundary condition here, you see this is F minus I minus Fi, yeah, and here I've forgotten here the post-collision thing. So you see this is kind of acting on a first order moment, because it's the difference between the one that is going in and is going out is equal to the velocity. Yeah, so would be minus 2 theta wi ei times ubc, right? So this sets a first order moment. the anti-bounce back boundary condition, this has here the sum of two moments. Yeah, so it sets a second order. It is a boundary condition for a second order, or say, so the one is for even, or say, no, this is for odd moments. Yeah, so one going this way is the opposite to this way. This is an odd moment, so first moment, third moment. This here, the anti-bounce back is a boundary condition for even moments, so 0 moment, second moment, which is either zero order or 0 moment or second moment. These are, energy pressure, density pressure, yeah? So we set the boundary condition for this, and we see this is supposed to be the equilibrium in the one direction plus the equilibrium in the opposite direction. Yeah, so so here we set basically this new population that we want to have, this Fi over bar here to this, to the equilibrium second or 0 moment, so basically setting the pressure. This is why this is a pressure boundary condition. So it basically sets the pressure. However, it also needs, for computing the equilibrium, it also needs to have a velocity. But this velocity, it only needs also at the second order, because think about it, what happens if you add the equilibrium population going in this direction and in the opposite direction? What components of velocity would that actually have? So, in the equilibrium, there's linear part of velocity, and then there is velocity square, right? Yeah? So, and the linear part in this direction is the opposite than in this direction, right? So if you add them up, the linear part will disappear. And there will only be the quadratic part left. Yeah? So, yes, the UBC, you still need the UBC in order to be accurate, but this you could, for example, get from extrapolation. So this is often done by just taking the nearest neighbor, the node next to the outlet, taking the next node from the outlet and setting the velocity to this value. Okay. Now we have velocity boundary conditions and we have pressure boundary conditions. But all these boundary conditions so far can be set only just in between lattice nodes, which is inconvenient. Therefore, we also need something that is called off-lattice boundary conditions. Okay. Off-lattice boundary conditions are usually only implemented for velocity boundary conditions. And the reason is the following. If you have a pressure boundary condition somewhere, this is usually at the end of your simulation domain, yeah, where you say, okay, this is here, I have to have an atmospheric boundary condition. And the location, the orientation, and whether this is a straight line or not is usually not really important for you, because it's a cutoff of your domain anyway. Yeah, but this is completely different to a velocity boundary condition, where you want, for example, to describe the surface of the car that you are simulating, of which you want to measure the track coefficient, right? So there you want to place the boundary condition accurately. And you don't want to build your boundary from Lego cubes. Yeah, you want to have, if there is a smooth surface, you want to have a smooth surface. If there is an inclined surface, you want to have an inclined surface, and this should not be a staircase. So now you need to find a way to impose such velocity boundaries, also moving velocity boundaries, thinking about, turning wheels, for example. Yeah, you want to impose this anywhere in between lattice nodes. And for this, you need this off-lattice interpolation methods. So this is then based on the bounce-back method, so interpolated bounce-back. And the first person coming up with these things was Bozidi, and the paper of Bozidi et al. In 2001. Who's old? Okay, I heard this is a question I'm not allowed to ask, but I always think about my students who was alive in 2001. Okay, so his idea was to introduce a subgrid distance that he called Q, and Q is the fraction of the distance EI, so this is the vector of this particular link, times delta x. So this is the lattice spacing between the last grid node and the actual boundary. So now in his method, he had to distinguish between two cases. Namely that Q is smaller than 1/2, yeah, and Q is larger or equal than 1/2. And by the way, Q always is in between 0 and 1, yeah, because 0 would mean that the boundary condition is directly on the wall, and 1 would mean that it's directly on the next one, yeah. So okay, this distinction. Now, unfortunately, I have to draw this, and let me see. We start with Q smaller than 1/2. So this is the boundary. Let's give some color. And this here, this distance, is delta x times Q. Of course, this is as always delta x, and this is as always delta t. And yes. So this is the wall, and now what we want is that the particle that arrives here, so the particle should arrive here, right? So when it has a bounce back on this location, that would mean that it would come from here. And this distance that we have here should be, even though I've not drawn it beautifully, but this should be 2q delta x, 2q delta x, right? And this node here is at xn. And this this would mean that we have to interpolate between, because not beautifully drawn. So these are the populations that we actually have, right? So now what we can do, we can interpolate between these two green populations in order to get the red population, and that red population would be the one that is going into this next time step down there. So this is done like this. We have the opposite facing population at the next time step. So plus delta t is then the linear interpolation between the two. So it's 2q fi after collision at the nodes xn and time t plus 1 minus 2q times fi star x n minus delta x ei and t. So this here is the position xn minus delta x ei. So this is this position here, right? So we linearly interpolate before we do the streaming. Then we stream, collide at the wall such that we arrive at the correct position. So this was case number 1. Then comes case number 2. Case number 2 is the case when Q is larger or equal to 0.5. So when the distance is larger, so what happens if the distance to the wall is larger? Then this would mean that we can no longer do the interpolation. Or let me first draw it and then explain. Say we are here and the wall now, the wall is here. And now we usually had the problem if you want to arrive here, we would try to interpolate. Yeah, so I'll briefly draw this and then I'll discard it again. Yeah, we would come from here, and this means we cannot interpolate them from these two nodes, right? So we have to do it in a different way. And the different way is the following. We start from here, having the bounce back here and ending up there. Then we can calculate that, okay, so this is xn, this is again x, and this is again t. We can calculate that this distance here becomes 2q minus 1 delta x. So now this is not enough because we want to have the population here. What we can do is we can take into account this population that goes the other way and now interpolate. So this here is obviously delta x, right? And now interpolate between this point and that point after the streaming. So now this works like this. So we have fi xn t t plus delta t is now the combined distance is 1 over 2 q fi star xn plus t plus 2q minus 1 divided by 2q fi star okay, I miswrote this on my this is the opposite. So, okay, over bar, fi over bar, right? Fi over bar of xn and t. Okay, I miswrote this, but I think, yes, I think this should be the right way. So I take the one that is already going in the fi over bar direction, whereas this here is fi, yeah. So I take the one that goes into the other side and combine this with this one and do the interpolation after the streaming. So in the first case, I do the interpolation before the streaming, and in the second case, I do the interpolation after streaming. Okay. Now, in principle, we have everything. So you can have a velocity in any particular point, and you can put the pressure boundary condition. There's one more thing. One more thing that I wanted to talk about, namely that we can also do this in a little bit of different fashion. Let me just go back. So the disadvantage of this method is kind of related to the distinguishing between this q smaller than 1/2 and q larger than 1/2. The problem here is that for this smaller than 1/2 case, we always need a neighbor. Yeah? So needing a neighbor is, depending on your neighbor, it's a good thing that you have neighbors, yeah, but depending on your neighbor is always can always be difficult, because so your neighbor, your neighbor must be at home, yeah, and there actually needs to be a neighbor. So okay, sounds stupid what I'm saying with your neighbor must be at home, but you have to think about the following. Your neighbor's data needs to be accessible, and it also needs to be in the correct state, right? And if you have a parallel, either you have a serial execution or a parallel execution. In a serial execution, you would think about, so have I updated this guy already, yeah, or not? And have I overwritten something important or not, yeah? So actually, depending on your algorithm, this data may not be available anymore, or it may be in an uncertain state. Therefore, you try to avoid using your neighbor as much as possible, because this helps you to make your code parallelizable and run it, for example, on things like GPUs more easily. So for this reason, we try to do the same thing as here, just with one point. This means without neighbor. So it's called a one-point interpolation. One-point interpolation bounce back. So this one-point interpolation bounce back is a method that has a few degrees of freedom that you can implement in a few different ways. So you'll find the same method in 5 versions coming with 10 people who claim that they invented it. Okay? So you now get one version that is not drastically different from all the others, and they all work roughly the same way and give roughly the same result. Let's draw the picture again. So having here an X and having here an T. And here are our nodes. And now we have a boundary someplace here. Here would still be the nodes. And we do not distinguish now between delta x larger than 1/2 or delta x smaller than 1/2. We just say this distance here is q delta x. And yes, so this distance is q delta x. And now we draw some, there's an ugly color. Now we draw here these outgoing populations. And one thing that we observe is when we have here a distance, q delta x, then the distance in time that it takes to reach the wall is obviously q delta t. Yeah? So let's call this here xn. Let's call this here xbc. So this is the position of the boundary. And this here is, okay, I just call this xa. And the node here I'll call x virtual because it is a node inside the wall. So, and what we do now, instead of interpolating just in space, is we are using linear interpolation along the characteristic. This means the characteristic is the thing that moves through space and time. So we use linear interpolation along a characteristic. So first of all, we have to get okay, let me see. Yeah, so first of all, we have to get to this position here on the wall. So what is Fi at the position of the boundary? So when we evaluate at the position at the boundary, we have to take this at time t plus q delta t, right? So this is on the boundary, and the position of the boundary is xn plus q delta t, and the time is t plus q delta. The position is xn plus q delta x, and the time is t plus q delta t. So this is the position at which we want to evaluate this, and this can be taken from the linear interpolation along the characteristic. So we take xn and t doing the linear interpolation. The distance is 1 over q, so this is the distance is q, so we have 1 minus q plus fi x v. This is the virtual, yeah. So this is the virtual distribution at t plus delta t times q. This is the linear interpolation along this characteristic to get to this point in space and time. So how do we get to this population at the virtual node? You see, this is a pre-collision. This is a pre-collision population in the virtual node at the next time step. How do we get this? So what is the pre-collision state here? This is the post-collision state there, right? You see this? This F. So Fi xv t plus delta t is equal to the post-collision at xn at time t, right? So we can basically plug this in and having then Fi at x at the boundary at t plus q delta t is equal to Fi xn and t 1 minus q plus Fi asterisk xn and t times q. Okay, so now everything just comes from this node so far, right? So now we apply a bounce back on the wall. Bounce back on the wall means we are returning this bounce back on wall means that this Fi over bar, so the one that is now coming in the opposite direction is xbc of t plus q delta t is equal to, it's just the same thing, xn t 1 minus q plus Fi after collision xn and t times q. Okay, now what we have is the pre-collision state at the boundary node. What we want to have is the pre-collision state at this xn position. So what we are now going to do is to interpolate between this F opposite here and this F opposite there. Yeah, here at position BC and here at position XA. So this means we do interpolation between Fi opposite XA at t plus delta t and Fi pre-collision xbc and t plus q delta t. So this interpolation in time and space along the characteristic. So basically what we are doing is we are interpolating to this point, which is in the right location, but not necessarily quite in the right at the right time. Yeah, so this actually becomes Fi over bar xn. Now this is now interpolated in time. Therefore, recharging ink I mean, we are lucky that I have two of them, right? Otherwise, I would be on the board. Okay, sorry. So Q plus 1 plus actually the same thing again, Q delta T Q plus 1. So we have to do this because we are interpolating in time. This is Fi x a and T plus delta T. Now this comes into Q divided by Q plus 1 plus Fi over bar xbc and T plus Q delta T into Q by Q plus 1. This thing here is something that we also know, because it's the pre-collision state in the next time step of our neighbor, and this is equal, because it's coming from us, it is equal to the post-collision state at the boundary node at the current time step. So we can hence combine all of this to say that this is Fi over bar of xn and T plus 2Q delta T divided by Q plus 1 is equal to Q divided by Q plus 1 Fi asterisk xn and T plus, now we introduce the one, let me see, we introduce now this here into the equation, having Fi xn and T times 1 minus Q divided by Q plus 1. I acknowledge there's a lot of Q's here. Fi after collision xn and T times, okay, I'll need some more space. Times Q divided by Q plus 1. Okay, so now this is all this interpolation that we had to add. Now, is this now a boundary condition? Now we get what we get after all of this is the incoming population at the right position, but we don't get it at the right time. Now, usually, so for several reasons that we will elaborate on Monday in particular, space resolution is a bigger problem than time resolution. And this is in particular also the case for the boundary, because on the boundary, the velocity usually does not change quickly. So, and by the way, we've just discussed about this delay bounce back. We just said, okay, we just return it one time step later, right? So this doesn't do much to the accuracy here. So when we want to place an accurate boundary condition, we mainly mean to place it at the right space, but not necessarily at the right time. That this doesn't make a big difference. So we can place the boundary condition at the right place if we can accept that we place it slightly at the wrong time. Therefore, we now, we say this is the second order, would be second order accurate because we use linear interpolation as second order accurate in space, but only first order in time. And I can tell you it's hard actually to observe that this makes any difference. Okay, I have not investigated it very, very carefully, but I'm not aware of any particular problem that arises from this thing. You simply specify now that we set at the forthcoming or even the over next time step that this becomes Fi over bar after collision xn and t plus Fi after collision xn and t, so times q by q plus 1 plus Fi xn and t, so this is the pre-collision state, 1 minus q divided by q plus 1. And it's your homework to determine how you can use this for doing a turning wheel. Yeah. So there's now one particular place, namely when you place the bounce back on the wall, you do a bounce back on the wall here, you would have to add the velocity shift that we previously introduced in the velocity bounce back. Yeah. If you introduce exactly the same thing here and go and put this within the interpolation, then you also get an off-grid velocity boundary condition with arbitrary velocities. Okay, so now this concludes the lecture on boundary conditions. Now the way it is going on is tomorrow, since we have taken today one lecture more than was planned, we'll have no lecture tomorrow. Instead, we'll have in the morning the combined exercise where we actually go through the entire code, which we can now do because we already talked about boundary conditions. Yeah, so we'll go through the entire code, and in the afternoon, you get some time to actually implement this code yourself, which is important because next week we'll have a hackathon, yeah, where you are supposed to implement another collision operator into this code. And for this, you would first of all have to have a code, and you also need to be familiar with this code, right? So this is what then we'll do tomorrow in the afternoon. So tomorrow more work for you and less work for me. Yeah, these ones.
Yes, little bit above.
A little bit.
Yeah, that is enough. What is the
Although,
difference
yeah.
between this bar terms and without bar? Like
What's the difference?
M20 bar and M20.
Yeah, you see, we introduced, you remember that we introduced F. Okay, okay, maybe I've not, maybe I was not, so we have introduced the same for the F's, right?
Yes.
Yes, the same, okay, it's the same thing, so this is the same thing for the moments as it is for the populations, right? So, and this MAB star is of course the sum over I and J, I by the power of A and J by the power of B into Fij asterisk, right?
So when it comes to the code, we just initialize M20, right? We don't initialize M20 bar.
We initialize M20, right? Yeah, so you would initialize M20 if you start with a collision.
Okay.
Yeah. So if you intend to start with a streaming, then you would have to initialize M20 star.
So will we have two arrays for each M? Or we just need one array?
we don't need an array for M at all because this is a local operator. We usually don't store the moments. We only store the populations. There's no reason to store the moments. Okay, so from the moments we compute the populations, the way that was discussed yesterday. Yeah. So this further step you have to do yourself. Yeah. So you still have to do the back transformation yourself.